The double-slit experiment stands as one of the most profound in physics. It offers a glimpse into the strange world of quantum mechanics, governing matter at atomic and subatomic levels. This experiment has captivated physicists and laypeople alike, challenging our understanding of reality. It demonstrates wave-particle duality of matter. Particles can exhibit both wave-like and particle-like properties. This notion contradicts our everyday experience. The experiment raises profound philosophical questions. In the following sections we will delve deeper into the double-slit experiment. Imagine a barrier with two closely spaced slits cut into it. Behind the barrier there is a screen that can detect particles. This forms the basis of the double-slit experiment. Let's consider electrons for this example. When fired at the barrier, one might expect two bands on the screen. However, this is not what happens. Instead, we observe an interference pattern. This pattern has alternating bright and dark fringes. Such a pattern is a hallmark of wave behavior. Waves passing through slits create interference. Bright fringes are due to constructive interference. Dark fringes represent destructive interference. The interference pattern suggests electrons exhibit wave-like behavior. The observation of an interference pattern in the double-slit experiment is surprising because it suggests that the electrons are passing through both slits simultaneously, just like waves. This is counterintuitive because our classical understanding of particles suggests they should only pass through one slit or the other. To further investigate this strange behavior, physicists devised a way to observe which slit each electron passes through. However, the act of observation introduces another layer of complexity to the experiment. When we try to determine which slit the electron goes through, the interference pattern disappears, and we are left with two distinct bands on the screen, as if the electrons were behaving like classical particles again. This perplexing result highlights a fundamental principle of quantum mechanics. The act of observation can influence the state of a quantum system. The very attempt to measure which slit the electron passes through forces it to choose a definite path, collapsing its wave-like nature and revealing its particle-like behavior. The double-slit experiment demonstrates that quantum entities like electrons do not possess definite properties until they are measured. Before measurement, they exist in a superposition of states, simultaneously embodying both wave-like and particle-like characteristics. Section 4. Wave-particle duality, the heart of the matter. The concept of wave-particle duality lies at the heart of quantum mechanics. It suggests that all matter possesses both wave-like and particle-like properties, despite our everyday experience suggesting otherwise. This duality is not limited to electrons. It has also been observed with other particles such as photons and even atoms. The wave-like nature of matter is evident in the interference pattern observed in the double-slit experiment. This pattern indicates that the particles are interfering with themselves, a characteristic of waves. The particle-like nature of matter is revealed when we try to observe which slit the particle passes through, causing the interference pattern to disappear. Wave-particle duality is a challenging concept to grasp because it defies our classical intuition. We are accustomed to thinking of waves and particles as distinct entities with distinct properties. However, quantum mechanics forces us to abandon this binary view and embrace the possibility that matter can exhibit both wave-like and particle-like behavior depending on the experimental setup. Section 5. A Journey Through Time. Historical Perspective. The double-slit experiment has a long and storied history, dating back to the early 19th century. In 1801, Thomas Young first demonstrated the wave nature of light using a double-slit experiment. His experiment provided crucial evidence for the wave theory of light, which had been debated for centuries. In the early 20th century, the advent of quantum mechanics breathed new life into the double-slit experiment. Physicists began to realize that the experiment could be used to study the wave-like properties of matter, not just light. In 1927, Clinton Davison and Lester Germer performed the double-slit experiment with electrons, confirming their wave-like nature. Since then, the double-slit experiment has been repeated countless times with ever-increasing sophistication, always yielding the same perplexing results. It has become a cornerstone of quantum mechanics and continues to inspire new generations of physicists. Section 6. Making sense of it all. Analogies from everyday life. Analogies can be helpful in understanding the counterintuitive concepts of quantum mechanics. One way to think about wave-particle duality is to imagine a coin spinning in the air. Before it lands, the coin is in a superposition of states, simultaneously representing both heads and tails. Only when it lands and we observe it does it collapse into a definite state, either heads or tails. Similarly, an electron in the double-slit experiment can be thought of as being in a superposition of states, passing through both slits simultaneously. Only when we try to observe which slit it passes through does it collapse into a definite state, going through one slit or the other. Another analogy is to imagine a ripple spreading out on the surface of a pond. If we drop two pebbles into the pond simultaneously, the ripples will interfere with each other, creating an interference pattern. Similarly, the wave-like nature of matter in the double-slit experiment can be thought of as ripples, spreading out from the two slits and interfering with each other. Section 7, The Enduring Legacy, Why the Double-Slit Experiment Still Matters. The double-slit experiment continues to be relevant today for several reasons. First, it provides a fundamental test of quantum mechanics, one of the most successful theories in physics. The experiment's results continue to be consistent with the predictions of quantum mechanics, further solidifying its foundations. Second, the double-slit experiment has implications for our understanding of the nature of reality. It suggests that the act of observation plays a crucial role in shaping the universe we observe. This has profound philosophical implications and raises questions about the role of consciousness in the cosmos. Third, the double-slit experiment has practical applications in various fields, including quantum computing and cryptography. Quantum computers, which exploit the principles of quantum mechanics, have the potential to revolutionize fields such as medicine, materials science, and artificial intelligence. In conclusion, the double-slit experiment stands as a testament to the strangeness and wonder of the quantum world. It challenges our classical intuition and forces us to reconsider the fundamental nature of reality. The experiment's enduring legacy lies in its ability to inspire new generations of physicists, philosophers, and anyone curious about the mysteries of the universe.